last one is post-processing. What does post-processing means is that when we are getting the outcome of the system, how we can actually make the decision. Most of the work on fairness for post-processing is called black boxing. Black boxing means that we don't know anything about the system. If we don't know anything about the system, how we can realize that the outcome is actually discriminative or not? So we have to go back to see if this is the outcome of the system, if there is something correlated to the input. We don't know what's happening between, and we cannot explain it. This is specifically the case for a neural network, for instance, because neural networks are not interpretable. So we cannot go back from a decision to say what was happening in between. So there are some people working on this black box to be able to explain the decision of, for example, neural network. How they are doing it, they're just mimicking the behavior of this black box with, for example, some interpretable models, decision trees. And then they are able to explain they are getting this outcome because of this procedure. And this is important because for some countries, like in Europe, you have to explain to the user why you are actually giving them this decision. So this explainable AI is actually important for those scenarios. So if you are interested, this is a very nice paper on black box post-processing fairness. The last one that I want to talk about is also my own work, which is in progress, but it's fairness verification. Fairness verification is a bit different than the pre-processing, post-processing, or in-processing. The verification is that when you have a deployed system, so there is this company, and they have this neural network model that I'm using, but they want to make sure that if they are deploying it, it is fair or not, they need some guarantee. So we have to verify that if we are actually using this system, there is no input that the system is unfair towards it. So this is a verification. It's a really nice property. So if we can verify a system, we can actually provide a guarantee. In the case of hiring, for instance, assume that there is this company that they want to use this neural network. And then using this neural network, they want to make sure that the gender of the applicant has no influence on the outcome. So they have this model, what they should do. If we consider group fairness, that means that we need to check for the populations of the male and female. The opportunity is the same for both of them. In terms of individual fairness, this is the work that I'm doing, is that I want to make sure that each female applicant, they have the same, probability of getting the positive decision as a male applicant. Individual fairness is pretty hard for verification because we have to check all pairs of individuals. And enumerating all pairs of individuals is very challenging to do. So here, assuming that we have this deep network, the input is set of features. The blue ones are non-sensitive, and the red ones are sensitive. So we have age and gender sensitive, experience and education non-sensitive. The outcome is coming from these two neurons. So if Y1 is more than Y2, we say that we are hiring that person, otherwise we are not hiring. So it's a binary classification. What I'm doing is that I'm creating deep verification network. What is the verification network? Because I want to compare two pairs, and I'm using a causal discrimination formulation. If you not remember it, causal discrimination is saying that if all the non-sensitive attributes are the same and only the sensitive attributes are different, the outcome should be the same. So what I'm verifying is that if you have these two networks, all the non-sensitive are the same. So they are sharing the neurons, and all the weights are the same. The non-sensitive, the sensitive one are different. So for example, we have a male young, but the education is high, education is low, experience is high. And we have another individual with the same experience and education level, but that's an old female. The outcome should be the same. So if we have any case that this Y1 more than Y2 and Y2 is less than Y1, we have the discrimination. So I need to search all of it. How I'm doing it, I'm actually converting this verification network to an optimization problem, and I'm and I'm running a satisfiability problem. So I'm just trying to satisfy it based on this property. So I convert all the neural networks, like all the neurons activations, to the mixed integer program. And then I have a system that I can actually verify the system. So if there is a counterexample, I can see that I cannot provide a guarantee.